Okay, let's go. We're ready. Started secondary last time.
I forgot about that.
Ended in kind of a weird place, I think, but let's just pick up. Sets. So we spoke about what a set was, some highlights, recall. So when we talk about set, it's a collection. It is unordered, has no repeats. We spoke about something called a tuple. Right? So the guys that look like this is things like A equals 1, 2, 3, which you can think of as equal to 2, 3, 1, etc. Doesn't matter, the order doesn't matter, and we don't have repeats. Tuples, they are also collections. They are ordered, and repeats matter. They're allowed and they matter. So it matters who's in the first position, the second position, the third position, etc. I can say T is a tuple and it could be 1, 2, 3. This is not considered the same as 2, 3, 1. It's not also the same as say 1, 1, 2, 3. Right? In fact, if I say an n set, this is just, I'm going to call this a new name now, set with n elements. N tuple. The tuple with n elements. So this is a 3 tuple, that's a 4 tuple. They're completely different. The order in which the guys appear matter, and repeats are allowed, and they actually make a difference. Something repeating twice, it actually matters. There are some things that it's useful to think of them as sets, other things it's useful to think of them as tuples, and for probability, we're going to go a step further. We're going to talk about similar objects today. But we're often going to think of sets, or sets of tuples, where we have sets that we throw into those sets, other sets, or we might throw into them other tuples. Yeah.
So, is this going to be at the midterm? What we're doing this next week?
Yes. Is yours Tuesday or Wednesday?
Wednesday.
Is it Wednesday? So everything up to tomorrow is going to be. And like I said, tomorrow I will post like a review for you guys to actually go over some stuff. Because I know we haven't been doing a lot of quizzes or anything like that, so I know you guys will need practice on that. But everything up to tomorrow is going to be part of that. So that it was a set, that was a tuple. I tell you what it means for two sets to be equal, right? They have the same elements. Did I tell you what an empty set was? No? Well, let's do that. Empty set. In fact, let's do the empty set. This is a set with no elements. Well, we're going to see how this set actually appears pretty soon. But the notation is going to be like a 0 with a strike through it, or right, just an open pair of brackets and don't write anything in. This is called the empty set. It's a very important set. It's a collection with nothing in it. Yeah, I mean, today's class and probably also most of tomorrow's is going to be a lot of definitions. We're learning about sets, so I'm going to have to be telling you what a lot of things are. So we're going through that kind of phase that we went through with matrices, where I'm just dumping a lot of information on you, but it's going to be necessary for tying everything together. Another definition. We say A is a subset. So I'm going to define the phrase subset of a set B if every element in A is also an element in B. And we write, well, there are two versions. We can write A subset of B, and A is a subset of B. Now these are almost the same thing. The distinction is the following. This is A is a subset of B. That's how you'd actually read it. A is a subset of B. But what this bar underneath means, it's potentially exactly the same, potentially equal to B. Not necessarily, but potentially. This one says that A is a proper subset of B. That's the phrase here. We call that symbol a proper subset, meaning A is a subset. And you write that when it's known not to be equal. If you're not sure whether it's equal or not, just write this. This includes that, but this doesn't give enough information as that one. A is not a subset of B. We write A is a subset. Let's do some examples. While I'm giving you definition, we'll just do some Mickey Mouse examples to make sure you're understanding what I'm writing down. So let's say A is 1, 2, 3, 4, 5. Let's do 5. B is C is C. So let's talk about the relationships between these sets. Let's relate A and B. Is B a subset of A? What about, is A a subset of B? No. Is D a subset of A?
Yes.
What about now? Is that okay?
Yeah.
Is E a subset of A?
No.
That's actually true. This is yes. Now, why that is, that's an exercise in logic. It's because the statement of what it means to be a subset is a logical statement called an implication. And it turns out that if the first part of the statement is false, you consider the whole thing to be true automatically. It's kind of this weird thing in logic, but it actually makes sense. Maybe I'll talk a little bit about that, but probably not much. I want you to note something very important. The empty set. Or let me state it in a different way. For any set A, we have the empty set is going to be a subset of that set. This is automatic. Now here's how we want to think of subsets, and it's probably better to think of it this way for probability. So what you want to think of a subset as is that you're making a sub-collection, meaning a collection already existed, and you're choosing things from that collection to create another collection. This other collection you create is called a subset. That's how you want to think about it. So you can notice that to create the set B, what I did was I went to the set A, I selected the element 1, I selected the element 3, I selected the element 5. Okay? And I didn't select 4, and I didn't select 2. Okay? And this is how this guy was created. So I can create this subset by selecting. Now, it turns out that it's possible to select nothing. This is an option you have, right? You can say, oh, choose whatever you want. And you're like, I don't want to choose it. That is a valid choice, right? So you can choose, hey, what subset do I want to create from this? Don't want to choose anybody. Essentially, you're by default choosing an empty set. I want to choose no one from that set. So this is automatic for everything. You have the option of choosing nothing. You can choose 1 or 2 or 3 or 4 or 5 things or no things from this set to create another collection. That's not the only reason how you can get an empty set. There are other ways. But here's another important idea. Also, that should also follow automatically, right? A set is a subset of itself, because everything in here is in there. So these two things you should be aware of. There are some dicey situations that if you're not aware of that, you'll get in trouble. Here's another important idea, just to compound on subsets. There's the idea of a power set. Now, the power set of a set is the set of all subsets of A. Now, this is a very, very important set. I'm not sure we're going to do a lot with it directly, but for sure, as an idea, the fact that a set can contain other sets is something that you do want to be aware of and not be confused by. So, let's say, for example, yes.
Would that, like, would their example that was right there, would that be like an equal or a subset? Like, would there be an
both are actually correct here. Well, you can have that, because that doesn't really make any sense.
Okay.
But it's definitely that.
So, how come in the example it didn't have like an underline?
Which example?
The one that you just erased.
For where?
For the empty set,
Yeah.
why is it underlined? Isn't that like assuming that it could be equal? But how
Because I'm saying any set. A could be the empty set itself, which is why I want the equal there, right? This sign means potentially equal to. I don't know if A is empty or not, right? This can work for anything, including the empty set itself. That's why I put the equal. This includes the fact that the empty set is considered a subset of itself. Yeah. Good. Yeah. Keep coming with questions like that. Anything that's not clear. So let's say that is a set. Now let's say I want to go in and I want to create every possible subset I can from this set. Well, I call this set notation here It's going to be very similar to a notation that we're going to use for probability, but the P is supposed to be like fancier. It's supposed to be a fancy P. Whereas with probability, it's just going to be a straight up uppercase P. But here, if I were to create the power set of A, remember, this is a set that will contain subsets of this set, right? Now remember how we're thinking of subsets. It's me creating sub-collections. So, I see a set with two things. I can make the choice. I don't want to choose anything. I have automatically created a subset, right? I took an empty bag and I didn't put anything in the bag. I just, okay, I'm happy with my bag, right? Or I can create a set that contains the element 1. So I'm going to select 1, put it in here. Or I can select the element 2 and put that in the set. Or I can go to A and I can select everything and put that in the set. And that's all the possibilities. These are all the possible ways that I can select sub-selections from the set A. I can select no elements, or I can select one element, or I can select both elements. Right? And there are two ways that I can select one element. Yeah?
Wouldn't 2, 1 also be a subset?
Right. 2, 1
okay.
is exactly the same as 1, 2. Sets do not care about order. If it were a tuple and I'm thinking of all possible tuples I create, then yeah, I'd have a 2, 1 and a 2, 2 and a 1, 1. Yeah.
Oh, so would I include 2, 1?
No, because it's a set.
Alright.
Right. So it's a power set. Sets do not care about order. It just cares about the actual elements that are contained. So that is the power set of A. Do these. Find the power set of that.
Is there a power tuple?
Yes. But we're, I don't think that phrase is actually defined. But yes, there's a set of all possible tuples that can be created of a certain size. You have to get very specific about it. Because remember, a tuple can allow repetitions, right? So even if I have like one guy in a set and say, how many tuples can I create from that? Well, I can create an infinite amount. I can have this, right? Because I can repeat, right? But there will be a limit on how much I can create of a particular size. How many tuples could I create of size 3? Well, only one of them, right? However, if I throw it here, how many tuples can I create of size 3 now, right? We'll get to that. We're getting into counting. That's a whole subtopic. We're going to count the power set, but that's not really the same thing. Tuples, it gets I have to give you like theorems for how to actually count them and how to make selections. Let's say C is the empty set. What is the power set? Let's say D is the set containing the empty set. What is the power set? And a follow-up question. Maybe. Yeah, it's a shopping cart. Ready? Anyway, go. Do these. Minute. let's begin. What are all possible subsets I can make from this?
Null set.
What?
The null.
The null set or the empty set?
Set. You A.
No.
Why can't you do A by itself?
Huh?
You can't do A by itself?
No.
Why?
You can do a set containing A.
That's what we said.
Oh, A by itself and a set with A in it. Completely different objects.
My bad.
Yeah,
Alright, so
they're-
B in a set
They're
by
very,
itself.
very different.
C
Wait,
is
why you did that?
I'm not messing with it. Very
That's what I
different.
wrote. Like,
To say
I
A
said
versus the set with A in it, they're
Right.
different things.
Yeah, that's what
Okay,
I wrote.
go.
Alright, B would just be
A
a
set containing B.
A set containing C, a set containing A and B, a set
A and B.
containing A and C, and then a final set containing A, B, and C.
What about
C.
C?
Ah,
C.
Yeah, you got it.
Careful.
I'll talk about conventions where you can list things to make sure you don't forget later. But that would be that guy. How many things are in here? 1, 2, 3, 4, 5, 6, 7, 8. Okay. C is the empty set. What is its power set? So create all subsets I can from the empty set. It's just the empty set. There's nothing to select. I have one choice. So the set containing the empty set is the power set of the empty set. What about if I have the set containing the empty set?
No set.
What is the power set?
No set.
What's the power set now?
The set containing the empty set.
Well, the empty set itself is automatically a subset of anything. Then I can select this element and throw him in a set. And that's the power set of the set containing the empty set. Now, here's a question. If A has n elements in it, how many elements are in the power set? What do you think?
N to the something.
N to the something.
Or
Hmm? Any guesses? Yeah.
N squared minus 1.
N squared minus 1 seems like a fair guess to me. Does that actually work? Okay, this has 3 things in it. 3 squared minus 1 is 8. Checks out. This has 0 things in it. 0 squared minus 1 is negative 1. Doesn't work. Remember, we create subsets by selection. What does it mean to actually select something? Well, let me tell you how it means. Here's how you'd explain it to a computer, what it means to select. For every element in the set, you're going to make a choice, yes or no, to create a subset, right? So, how did this guy get created? Well, for every element, you answered no. How did this guy get created? Yes, no. How did this guy get created? No, yes. How did this guy created? Yes, yes, right? You're making 2 choices for each element, right? How many total choices can be made? Yeah?
Is it 2 to the n?
It is going to be 2 to the n. Now, that is going to be one of the counting principles we're going to do. If you have a certain number of things and you're making a certain number of choices for that number of things, the total number of choices will be m to the n, where the number of choices will be the base. Okay, so if you're making 2 choices, that means for each element you have 2 choices. So for the total, you have 4 choices, right? Because for any guy, you can either choose yes or no. How is this going to actually play out? It means that if you had 1 and 2, basically you'd have to multiply the choices, right? Because you can have a yes and a yes, or you can have a yes and a no, or you can have a no and a yes, or you can have a no and a no, right? So it's not just you're doubling, you're actually going even further. Because for each choice you make here, you can make a bunch of choices for the other guy, and then you can actually start to permute the choices. Don't worry, we'll get to that. I just wanted you guys to start thinking about this idea. When we get into counting, we're going to be doing a lot of that kind of thinking. It's going to be a little bit abstract, but start to get your practice now. It's going to be 2 to the n. You'll notice that this always works. 3, 2 to the 3 is 8. There are 0 elements in here. 2 to the 0 is 1. There's 1 element there. There's 1 element in here. 2 to the 1 is 2. There are 2 elements in here. The power set is always going to be the size 2 to the n. In fact, the power set is always larger than any set. This brings up the notion of size, and size is very important. Probability is all about actually accounting for size. So A is a set. The size of the set is denoted, but like absolute values are on the A. Sometimes they do this little thing here, and it's called the cardinality of the set. Because size doesn't quite do it justice when you start talking about infinite sets, which we're not, but things can get really sketchy in sets. If A has a finite number of elements, say n elements, where n is some natural number, some whole number, we can say the cardinality of A is n. That's the size of A, that's the number of things in A. This is the cardinality of A. You can also call it the size of A. It's basically just the number of things in A. If A is finite. The notion of size becomes a little bit more subtle when you start talking about infinite sets, like the set of all real numbers or the set of all fractions or something like that. But whenever our set is finite, it is just the number of things in that set. And so the above fact can be stated as, if the size of A is n, then the size of the power set of A, let's put it in another line, the power set of A is going to be 2 to the n. And that's how we can express that idea. Now, 2 sets can have the same size, and we call them equivalent to distinguish from the word equal. Sets A and B are called We often leave out the word numerically, but numerically is often also used numerically equivalent. If the size of A is the same as the size of B. Example. Here I have two sets, 1, 2, 3, let B be A, B, C. I want you to note, these two sets are not the same. A is not the same as B, but they are equivalent when it comes to measuring how many things are in them. The size of A is the same as size of B, and so we say A and B are equivalent. Equivalent because there are many contexts in which the actual elements in the set don't matter to us as much as how many elements there are in the set. And so if one set is very complicated to work with because you're not even sure who everyone is, but you can reliably think of some other set that is equivalent to that, you can often do a lot of math with this set over here and answer questions about that set over there. So there are many ways in which the size makes them equivalent, and we can study one set by studying another set. Again, we're going to do that in probability. We're picking up bits and pieces here and there. And there's some notation that I'll always use, but books and other places might use other things. And we write, you can write this to say that they're equivalent, or you can write this. That's also used a lot. Now, here are some common sets that you should know. So we have a set called bold-faced N. This is called the natural numbers. Pretty much what it's going to be. It's a set of all the positive whole numbers. 1, 2, 3, 4, dot, 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 forever. Some sources will include 0, but I'm not including 0. And it's a toss-up whether or not what you're reading actually counts 0 or not. But the appendix or somewhere is going to tell you. Anything that deals with sets very heavily, they're going to tell you. Another thing is bold-faced Z. This is called the integers. So this is the set of all the whole numbers. It includes 0, plus or minus 1, plus or minus 2, plus or minus 3, forever. So it's 0, 1, 2, 3, 4 going that way, and then minus 1, minus 2, minus 3 going that way, and you get what we call the integers. The Z is because of it's named after the German word Zahl, which means number. Another set that you should know is set Q, bold-faced Q. It's called the rational numbers. Distinguished from the crazy ones. But no, the root word here is ratio. It just means we're taking a ratio of the numbers, a ratio of the Zahls in particular. These are things that look like A divided by B, such that A and B are elements of the integers, and our B is not 0. So all possible fractions. We also call these guys the fractions. Another set is the real numbers. Now this one is very hard to describe. But for us, we can say something like x, set of x such that x is a point on the number line. any point. You can choose anywhere. There are no gaps with the real numbers. Or we can say x is a decimal expansion. So pretty much any point on the number line. There's C for the complex numbers. We don't have to know about that. We have these guys. And the following are true. How many things are in here? Infinity, right? So the size of n is infinite, but it turns out that there are the same number of things in there as in the size of Z, which seems crazy to a lot of people because doesn't that have twice as many things? I mean, it has all the positives and the negatives. How are they the same size? They're the same size. Even weirder, probably. That's all equivalent to Q. These are all infinities, but they are the same kind of infinity. The real numbers are different, though. The real numbers are larger. They are not numerically equivalent to all the others. So you should be aware of that. Of certain sizes and certain numbers that you can, sets that you can choose from. These are very common. You'll see them when you're reading in maybe your homework or a textbook or something. And in fact, I think I even used this before. When we were talking about systems of equations, I said, oh, we can have an infinite many solutions, and I can say, we said Z was an element of that. Remember we had that notation? So, that's it. But yeah, any point on the number line, you draw a number line, you can pick any point without restriction. You land on a point, you landed on a real number. It turns out that if you plot all of these other numbers, you'll have gaps, right? So if you start to plot like this on a number line, right, you're at a 0 or a 1 or a 2 or a -1. If someone points here, it's not on an integer, right? There's a whole space between these, right? And you can start to put in more numbers and more numbers. And it turns out that all these numbers here will have gaps on the number line, but the real numbers won't. And yeah. What else do I need to tell you? Okay, so I told you about cardinality, which is the size of sets, equivalent sets, the common sets. I told what tuples were, empty sets, subsets, maybe the universal set.
Jhevon?
Yes.
What is that thing between like the T and the Z? Yeah.
This? Didn't I define this last time?
I can't find it. I'm gonna list it though.
I thought I did. This means is a member of or belongs to. So if I have A is the set 1, 2, 3, then I could say, for example, 1 is an element of A. Or I could say 3 is an element of A. But 5 is not an element of A. So that's just a fancy, it just means is a member of, is an element of, belongs to the set, blah, blah, blah.
Thank you.
Now, sets are not considered in a vacuum. We always think of the sets as belonging to some universe. This larger set can vary by context. It's called a universal set. So every set that I write down, you can think of it as belonging to some universe. Now, this may or may not be stated, but you always imagine that this is the case. It's denoted by fancy U. So no set just exists on its own, right? Once I write down a set, you can imagine this was chosen from some other universe. Like I could imagine that, yeah, there's the integers in the background, but we're just considering these three out of that universe. So there's always like a background universe where your sets exist. They're not existing on their own. And that's all, and that idea, again, is something that generalizes to probability. There's something called the sample space of a probability problem. Every time you look at a probability, there's some set in the background that is dictating how you're doing your calculations. And that's called the sample space. So there's always some background set that has everything you need in it. You can create sets from it and do stuff with it. One thing we do want to also define in this regard is the complement. The complement of a set A. Is the set of all elements that are in U but not in A. This is denoted, you can call it A complement, A with a little c, or A complement, A with a little apostrophe, or sometimes you put A bar. These all represent the same thing. These are called the complement of A. Or sometimes I'll just say A complement. And this is what I'm talking about. So, for example, let's say for the context of a particular problem, I consider the entire universe, everything in existence is 1, 2, 3, 4, 5, 6, right? So I'm working in a universe where there are literally only 6 things. Now, when I'm in that universe, I'm considering the set 2, 5, 6, right? So then the question is, what is a complement? It is going to be the set of things, the set of all elements that are in U but not in A. So if I say A belongs to this universe, when I'm looking at A, I'm potentially missing some other people from the universe. Who are those people? Well, 1, 3, 4. That's it, right? So that would be your A complement. One way we can visualize this is via the so-called Venn diagram. Right? So this is a picture comprised of a box which represents the universal set. And I can think of sets being in this box represented as circles or ovals. So I can say in this situation, the universe has the numbers 1, 2, 3, 4, what was in A? The 2, the 5, and the 6 are contained in that group, but the 1, the 3, and the 4 are outside, right? So I have this entire universe where I have 6 things floating around. I collected a group of these things, and I call that group A, right? But they exist in a larger picture, right? So that picture is called a Venn diagram. The box will represent the universal set. Sets in the universe are represented by circles or ovals. Now, often we focus on cardinality in this case. So, for example, if I say U is 1, 2, 3, let's make it a little bit more. A, B, C, D, E, and my set A is the set of A, B, and C, then notice that the size of the universe is what? 5. What is the size of A? 3. So, a lot of times, we're not going to list the elements specifically. We're going to use the Venn diagram to talk about how many elements are in each group. So, the Venn diagram that will typically be drawn in relation to this kind of example would be, I'd have the set A here, and I would say there are 3 things in here, and there are 2 things left out here, right? So this is to say, i.e., there are 3 elements in A and 2 outside of A. And notice that for a total of 5 elements. So there are 5 elements in existence. 3 of them are in the group A, 2 of them are not in group A. And I can represent that idea by this, a Venn diagram. So rather than list the individual elements, we just list numbers that represent the number of things that are in a certain space. And we'll pick up with that next time, which I guess to that end, I might as well pass these around now. We'll get to these tomorrow. Some problems on Venn diagrams after we learn about operations on sets. I'll stop there for now. We'll do a few more definitions, but I think next time we'll start actually working on something.
We didn't get it.
Well, there are some extras over here.